Okay, so have you ever stopped to think about how we get a computer, a machine that's built on pure, cold logic, to actually understand language the way we do? You know, with all its weird quirks and subtleties. Well, in this explainer, we're going to dive into a really fascinating idea for solving that exact puzzle: teaching logic to finally speak our language.
Take a phrase like this. We hear it and we get it instantly. We know it means that just because something looks good on the surface doesn't mean it actually is. It's a statement about some things, not all things. But for a traditional by-the-book logic system, this sentence is a headache. It gets all tangled up trying to figure out what all is doing there when we clearly don't mean everything.
And that's the big question, right? How can we build a system of logic that doesn't just see the world in black and white, true or false, but can actually understand the shades of gray in how we talk? How can it grasp what we mean, not just the literal words we say? This is one of the biggest challenges logicians are working on today.
So to really get the solution, we first need to understand the problem at its core. Let's break down why traditional logic has such a tough time with something that seems so simple to us.
Okay, so here's the crucial shift in thinking. For a long time, logic was all about something called truth conditions. It would look at a sentence and just ask one question: is this statement factually true or is it false? But a new approach is flipping the script entirely. It asks a completely different question. It says meaning isn't about whether something's true out there in the world. No, meaning is all about how you can use a statement in an argument. It's a massive shift from what a word is to what a word does.
And this whole new way of looking at things has a name, and it's a really powerful one. The basic idea is that to understand language, you have to watch how the game is played, not just stare at the pieces on the board. It's called proof-theoretic semantics, or PTS for short, and this is where it all clicks. Think about a knight in chess. You don't know what a knight is by reading its dictionary definition, right? You know what it is because you know its moves, that L shape. Its meaning is its function. Well, PTS says we should treat words in our language the same way. The meaning of all, or and, or if, it's just the role that word plays in building a solid argument. So, how does this new meaning is use idea work when you actually apply it? Well, that brings us to the main event, a brilliant new take on some of the most important and trickiest words we use, quantifiers like all, some, and every. Here is the big idea, and it's so intuitive. Stop treating these words like clunky, separate tools that you just bolt onto a sentence. Instead, look at them for what they really are in our language. They're part of the connective tissue. They're called subnectors, which is just a fancy way of saying they are connectors that work inside the sentence, weaving ideas together smoothly, just like we do when we talk. Now, this isn't just some random thought experiment. This is a serious field of research. A logician named Nissim Frances is a huge figure here, and he calls his work a logic inspired by natural language. He's one of the key people trying to build this more intuitive, language-first approach from the ground up.
And you know what? This approach is incredibly useful. It's not just a one-trick pony. Thinking of quantifiers as subnectors helps solve a whole bunch of other tricky language puzzles. For example, contextual domain restriction. That's just a technical term for how we understand that when someone says everyone is here, they mean everyone in this room, not literally everyone on the planet. Or intentional transitive verbs. Those are tricky words like seek or need, where you can be looking for something that doesn't even exist. This model helps make sense of that, logically.
But it's really important to see the bigger picture here. This subnector idea, as cool as it is part of a much larger conversation. The whole world of logic is buzzing right now, with all sorts of different teams trying to climb this same mountain from different sides.
The subnector concept is a fantastic approach for sure, but it is not the only new idea on the block. Researchers all over the world are trying out all kinds of creative ways to solve this quantifier problem, and each approach has its own unique angle.
For instance, you've got modal logic, where they treat a word like everything as being kind of similar to a logical concept like necessity. Then there's nominal logic, which comes at it from a completely different direction, creating a special quantifier just to handle brand new concepts. And then you get into the really abstract stuff like categorical logic, which sees quantifiers as these complex mathematical things called adjoints. The point is, there are a ton of different ideas competing, which just shows you how vibrant and exciting this field is right now.
So after going through all this theory, you might be asking yourself, okay, but what's the point? Why does it matter so much if logicians get this right? Well, it turns out the implications go way, way beyond academic papers.
It all builds towards something really big. So step one, the goal. Close that gap between rigid, formal logic and the messy, nuanced way we actually talk. Step 2, the impact. Once you do that, you can create logical systems that are not only way more powerful, but also way more intuitive for us to work with. And step 3, the future, we're talking about revolutionizing how humans and computers communicate and even reason together.
So I'll leave you with this thought. Don't just think about asking a computer for facts. Imagine, what if a computer could truly grasp the subtle difference between some, most, and every? What kind of new ideas, new collaborations, new discoveries could we unlock then? What could we really build together? That's the future this kind of research is trying to build.